And welcome to Lesson 5-9. This is actually the last lesson for Unit 5. And today we're talking about integration and inverse trig functions. So as you may recall, back when we were learning derivatives, there were only two inverse trig functions whose derivatives you were expected to learn. And that was for inverse sine or arcsine, and for inverse tangent or arctangent. And the same is true for inverse trig functions and integration. The only two integrals for inverse trig that you need to know are the ones that would lead us back to inverse sine and inverse tangent. So this is what they look like, and they are slightly different from the derivative rules. So just do make sure that you memorize these. So here's what they look like. And I did write them both ways, both as arc and inverse, just to make sure you've seen both. So for the first one, we have the integral of 1 over the square root of a squared minus u squared du, where a is a constant. And that's going to actually be the arcsine of u over a plus c, or alternatively, the inverse sine of u over a plus c. And then for the second one, we have the integral of 1 over a squared plus u squared du. And that leads to 1 over a arctangent of u over a plus c, or alternatively, 1 over a inverse tangent of u over a plus c. Now, in terms of the two integrals that you have here, notice that for the first one, we have a radical in the denominator. The second one does not. And then notice for the one in the radical that it's subtraction as opposed to addition. And do take note of the order of the subtraction. Notice that it's the constant squared minus the function in terms of u squared, as opposed to addition, which technically could be written either way. So please feel free to understand that the denominator for the second one can be flipped around and it means the same thing. But for the denominator of the first one, it has to be that order because it's subtraction. Okay, so we're just going to look at a few examples here and then be on our way. All right, so we're going to start with this example here. So we're going to integrate the integral of 7 over the square root of 16 minus 9x squared dx. Now, eventually, I will talk a little bit more about how should you look at this and recognize that this is going to lead to an inverse trig function as opposed to something else you've done. So I will address that at the end of this lesson. But knowing that right now I'm focusing on the inverse trig, we should recognize that because I have a radical in the denominator and its subtraction, that this is the one that's going to lead to inverse sine. So first thing we want to do, though, is make sure that we match the form that we're looking for. So I'm going to move that 7 out in front. So I have 7 times the integral of 1 over the square root of. Now remember, inside the radical, we want this to be some constant squared minus some function squared. So that means I want to rewrite the 16 as a constant squared. Well, 16 is clearly just 4 squared. Minus, and then for 9x squared, I want to rewrite that as some quantity being squared. Well, 9x squared is really 3x quantity squared. So let me draw that radical a little longer. All right, and then dx. Now, the reason we would want to do that, this now, right here, is your u. So that means we know that our u is going to be 3x. So that means du will be 3 dx, or in other words, dx becomes du over 3. So now, when we substitute, we're going to have 7 times the integral of 1 over the square root of 4 squared minus u squared du over 3. du over 3. And then that 1 over 3, I'm going to go ahead and move that out in front also. So now in my integral, I now have 7 thirds times the integral of 1 over the square root of 4 squared minus u squared du. And now this integral matches exactly the formula that I showed you in the beginning of the lesson. So this now becomes 7 thirds times the inverse sine of, remember, it's u over a, but my a in this case is 4, and then plus c. And then finally, we're going to substitute back in for u, and we can get 7/3 times the inverse sine of 3x over 4 plus c. And that's our answer. And again, you are welcome to have written this as arcsine. I do think that WebAssign tends to favor the inverse notation as opposed to arc, but technically if you're able to type in arcsine, it should accept that as well. But if you do try typing in arcsine and you're sure you're right but it marks you wrong, try switching to the inverse notation to see if that makes a difference. All right, let's try another one. All right, so for our second example, we have the integral of x over the square root of 6 minus x to the fourth dx. Now, looking at this, some of you might initially think, wait, there's an x in that numerator, so this already doesn't quite seem to match the inverse sine that we've been looking at so far. But again, just kind of follow along and see what happens here. So first thing again that I'm going to do is I'm going to rewrite this so that I've got x over the square root of, and remember inside the radical, I want to write this as a squared minus u squared. So 6 is really the square root of 6 squared minus, and then x to the fourth, remember, is really just x squared squared. So that means our u is going to be x squared. Our du is therefore going to be 2x dx, or in other words, our dx becomes du over 2x. And that's why that x in the numerator is going to be okay, because that's going to cancel out with this x that I have in my dx. All right, so now let's go ahead and do some substitutions here. So I've got x over the square root of the square root of 6 squared minus u squared, and then this is du over 2x. So as I said before, the x's do divide out. That 1/2, I'm going to go ahead and move out in front. And we have 1/2 times the integral of 1 over the square root of 6 squared minus u squared du. And now we are matching exactly what we want for that inverse sine. So finally, this becomes 1/2 times the arcsine. I'm just going to switch up the notation here for practice. The arcsine of u over the square root of 6. Do not worry about rationalizing that. It's a waste of your time. So just leave it with a root 6 in the denominator here. But we are going to have to replace that u back. So we get finally 1/2 times the arcsine of x squared over the square root of 6 plus c. All right, so that's a couple of examples involving arcsine. All right, so let's go ahead and take a look at a fairly straightforward one here involving arctangent. So we have the integral of 6 over 4 plus 25x squared. And just like before, first thing I'm going to do is rewrite this, because remember that we want the denominator to match a squared plus u squared. So I'm going to rewrite this as the 6, I'm going to bring out in front, times the integral of 1 over, remember 4 is really 2 squared, plus, and then 25x squared is really 5x quantity squared dx. And so that means now we know that 5x must be our u. So u equals 5x, so du equals 5 dx, or in other words, dx equals du over 5. So when we substitute, that's going to give us 6 times the integral of 1 over 2 squared plus u squared, and then du over 5. And just like before, that 1/5, I'm going to move out in front to multiply with the 6 that's already out there. So now I'm going to have 6 over 5 times the integral of 1 over 2 squared plus u squared du. And now our integral matches exactly what we want for inverse tangent. So this now becomes, when we integrate, 6/5, which was already there, times. Now remember, for arctangent, this has that additional 1 over a factor in front. So it's going to be 1 over 2, because 2 is our a, times the arctangent, or inverse tangent, of u over a, so u over 2, plus c. And then finally, we just clean this up by substituting back in for u, and the 6/5 times 1/2. The 6 and the 2 are going to divide out to a 3 and a 1. So we finally get 3/5 times the arctangent of 5x over 2 plus c. And like I said, arctangent should be acceptable if you're able to type that in for your answer. Otherwise, use inverse tangent. All right, moving on. Okay, so now your homework will not actually have a problem quite like this one, but this kind of a problem should have appeared in your homework. There just wasn't any for me to choose from, but it's important for you to have seen this. So again, looking at this problem, this is very different from either of the two formulas I showed you. But if I'm supposed to try to apply either inverse sine or inverse tangent, I have to sort of make it match that. Now notice the big difference right now in the numerator, we've got two terms. So right away, this is different. Now, if I were to let u equal my entire denominator, that would only give me a 2x, which means I still have extra stuff up there in the numerator. So in a situation like this, one of the things that would be worth trying is separating the fraction into an 8x over 4 plus x squared dx, and then plus 1 over 4 plus x squared dx. And so the reason we would consider doing that is now how you would approach each of these separate integrals is going to be a slightly different method. For this first one, I would let u equal my entire denominator. So for this first one, I'm going to let u equal 4 plus x squared. So that means du is going to be 2x dx, or in other words, dx becomes du over 2x. So that means I would now have the integral of 8x over u times du over 2x. I'm going to come back to that second integral in just a moment. So now this would become, the x's divide out, the 8 and the 2 divide to become a 4. So now I can move the 4 out in front, and I just have 1 over u du. And so now we can just integrate this using our 1 over u formula, which is just going to be 4 times the natural log of the absolute value of u. Now I don't need to put plus c, because remember, we're still going to get that plus c from doing the second integral anyway. And then finally, of course, we would have 4 times the natural log of the absolute value of 4 plus x squared. And just a side note, 4 plus x squared is always going to be positive, so we don't need the absolute value here, but I'm not going to make us worry about that at this moment. Now for the second one, this does exactly match, or almost exactly match, what we would want for inverse tangent. We'd have 1 over 2 squared plus x squared dx. Now notice, that's just a plain x. It's not 2x, it's not 3x, it's not some function of x, it's just x. So we don't need to do anything tricky there. In other words, because it's just an x, I don't have to do a substitution, because otherwise I would just be letting my substitution equal x, and you're literally just swapping variables. So this just becomes the arctangent. Oops, I should switch to an actual pen. So the inverse tangent or arctangent. Oops, sorry. So 1 over a, so times the inverse tangent of u, which is just an x, over a, which is our 2, and then plus c. And then we could just bring that all the way down. And finally here we get 1/2 times the inverse tangent of x over 2 plus c. So again, you will not encounter this on tonight's homework that goes along with this lesson, but I did want to make sure that you saw that this is something to consider if you have an integrand that seems a little bit more complex than what you've done before. That if you have the opportunity in a fraction like this to maybe break it up into the sum or the difference of separate fractions, then that might allow you to approach this problem in smaller chunks where you're using a different integration technique on each part. All right, and then finally, let's wrap up with an evaluate question. So again, we're just going to evaluate this definite integral, but this time the antiderivative will involve an inverse trig function. So once again, I see the square root in the denominator, and it's a constant minus something getting squared. So that means I am going to try to rewrite this first so that it more closely resembles the inverse sine formula that we want. So I have the integral from 0 to 1/4 of 8 over, and again, you could have moved the 8 out in front if you wanted, over the square root of 1 squared minus 4x quantity squared dx. So now it's clear that our u is going to equal 4x, which means our du equals 4 dx, or dx equals du over 4. But remember, since this is a definite integral, we also need to change our limits. So when x is 0, u is going to be 4 times 0, which is still 0. But when x is 1/4, then u will equal 4 times 1/4, which is just 1. So this now becomes, I'm going to go ahead and move the 8 out in front. I have 8 times the definite integral from 0 to 1 of 1 over the square root of 1 squared minus u squared times du over 4. And then now I can move that 1/4 out in front to multiply with the 8. So 8 times 1/4 just becomes 2 times the integral from 0 to 1 of 1 over the square root of 1 squared minus u squared du. So now that exactly matches what we want for inverse sine. So now we're going to get 2 times, all right, so this antiderivative, remember, is just inverse sine of u over a, so that's just u over 1. So I'm just going to say inverse sine of u from 0 to 1. And that means I have 2 times the inverse sine of 1 minus the inverse sine of 0. Now remember, inverse sine is only going to have an output between negative pi halves and pi halves. So inverse sine of 1, remember that's asking the sine of what angle equals positive 1. But that angle has to be between negative pi halves and pi halves, just as a reminder there. So that would have to be pi halves. So we get 2 times pi halves minus, now inverse sine of 0, that's asking sine of what angle gives you 0. Well, and it has to be between negative pi halves and pi halves, so that's going to just be 0. And then finally, I have 2 times pi halves, which just gives me pi. All right. So that is integration that leads to either an inverse sine or an inverse tangent. Now, I do want to wrap up, though, because this is the end of our integration technique lesson, or unit, and I do want to wrap up just with 3 integrals that look sort of similar to each other, but they're very different from each other, and I want you at least to start thinking about how you can start recognizing when one method might work versus a different method. Okay, so I'd like to wrap up by having you consider these 3 different integrals. So the first one, 9 plus x to the 4th over x cubed, versus the integral of x cubed over 9 plus x to the 4th, and then finally versus the integral of x over 9 plus x to the 4th. So all of these look very similar, but the approach you would take on each of them is very, very different. So what I would want you to notice in the first situation is, in the first one, we're just dividing by a single term that's a power of x. And in a situation like that, what I would expect you to do is to rewrite this as x to the negative 3rd times 9 plus x to the 4th dx, so that now you can just distribute the x to the negative third, and you would have the integral of 9x to the negative third plus just an x to the first dx. And now you could just integrate this term by term using the reverse power rule. So again, this is something that I would expect you to try to look for if you notice we're dividing by a single term. Another alternatively, and some of you have already discussed this or described this or discovered it, but another approach to doing the same effect is rewriting this so that you're just dividing each term in the numerator by the denominator. So this becomes 9 over x cubed plus x to the fourth over x cubed. And then you can simplify from there. So it's going to lead to the same place, but it's just a slightly different way of getting there. And that's totally valid. Now, for the second one, this kind of looks like the inverse tangent that we just looked at today. But what I want you to notice is, if you were just to let u equal x squared, like we would have for an inverse tangent, if you were to let u equal x squared, then that means your du would just be a 2x dx. And the problem then is your dx would be du over 2x. And when you substitute, yes, that x will divide with one of those x's, but you're still going to have two x squared x factors left over in the numerator, and you don't want that. So this is a situation where what I would want you to notice is that the power in the denominator is only 1 degree smaller, or larger, sorry. The power in the denominator is only 1 degree larger than the power in the numerator. And if that's the case, that's when I would want you to recognize that most likely your u should be that denominator. Because remember, if that's your u, then your du is going to drop by 1 degree, and it's going to become 4x cubed dx. Or in other words, dx becomes du over 4x to the third, and so now your x to the thirds will divide out when you substitute. So you would have an x to the third over a u, and then du over 4x to the third. Now those x to the thirds go away. The 1/4 can come out in front, and you just have the integral of 1 over u du. And then finally, now compare that to this last one. Again, I have an x to the fourth in the denominator, but I have an x to the first in the numerator. Notice that those powers are more than 1 degree off from each other. So this is where you might recognize that this is maybe more like the inverse tangent, that you don't want to just let your denominator be your u. So this is where you would then consider rewriting this as x over 3 squared plus x squared squared, and then recognize that your u is just the x squared. And so your du would be 2x dx, or in other words, dx becomes du over 2x. And so now that x will divide out with that remaining x. So again, I just wanted you to think about, because now that you've seen all these different methods for integration, I wanted you to think about what makes these integrands similar, but more importantly, what makes them different that might help you indicate which method to use as you approach these. Because that will end up being one of the hardest things. Each of these methods on their own aren't necessarily super difficult, but trying to decide which method to use when all the directions say is integrate, that's a little bit more challenging. Okay, good luck.